Morning. Okay, good morning everybody, and hello everybody watching on the live stream. So sorry about Monday's class. Something came up as I was leaving the house that I had to take care of, and I couldn't make it to campus on time, which is why you got that very, very late message about the class. Sorry about that if you came to campus just for that lecture. If you haven't seen it, assignment 3 is out. Labs 4 and 5 are tied to assignment 3. They'll come out later tomorrow, I think. They're very short, but they will. Well, they use assignment 3 as the basis for the labs. I'm just going to quickly review what we were talking about before reading week. So I'm going to very quickly go through the first 30 slides of this or so, and then we'll carry on with the next part of the lecture. So we were talking about preconditions. We were talking about preconditions in the previous lecture. So remember that a precondition is, well, a condition is anything that's true or false, right? So it's just a Boolean expression. A precondition is some condition on a method or a constructor that has to be true for the method or constructor to run successfully. Right? So in other words, that condition has to be true before the method runs. Right? So when you call the method, that condition has to be true. Now, because that condition has to be true when you call the method, it's the responsibility of the caller to ensure that that condition is true. Right? So for example, if you try to divide a number by 0, so if you look at the point 2 class, there's a method called divide. Divide simply divides the coordinates of a point by the specified value. You can't divide by 0, right, successfully. So that method might have a precondition where the value that you're dividing by can't be 0. Right? So if a method has a precondition, that should be documented. Right? So when you write the documentation for your method, as part of the contract for the method, you have to tell people, hey, you can't divide by 0. Right? So in your Java doc, you might write something like, where you document the parameter. Right? You might write something like, that value must not be equal to 0. So that's fine. Now, because the responsibility of meeting the precondition lies on the caller, it's the caller's responsibility, right, for meeting the precondition. So as the implementer of the method, you don't have to care if the precondition is satisfied. Right? So in other words, you can do whatever you want if the precondition is not satisfied when you're implementing the method. Right? So you can simply ignore the case where s is equal to 0, right, and just go ahead and divide. Right? So that's a perfectly legitimate way of implementing this method. Right? Now the problem if you do that sort of thing is that when your method runs, it runs with an invalid input. Right? And all sorts of things can happen at this point. Right? So for example, if your method promises to return a value, it might return the wrong value. Right? If your method might encounter some sort of error, right? Which won't happen in this case. If you divide by 0, there's no error that's caused. But some other precondition might, violating some other precondition might cause some sort of error, right? So your program might crash. Another consequence is that your method can't do everything that it says it does in its contract, right? So in other words, it doesn't satisfy its postconditions, which is what we're going to talk about next. And another possible consequence is that the method can put an object into an invalid state. So if you divide a point by 0, right, so if I take that point, divide it by 0, you end up with infinity and infinity. Right? You can also end up with negative infinity, or you can end up with not a number, right, nan. All of which you might argue, depending on what your point class is being used for, you might argue that those are invalid points. Right? Okay, so if you have a precondition on a method or a constructor, then normally what's done in Java is that you throw an exception if the precondition is not satisfied. Right? So an exception, you've seen these already in the assignments and in the labs, right? So an exception is just short for an exceptional event. An exception is actually an object in Java, and that object can carry information about the error or the thing that happened. Right? So if you ever get an exception in Eclipse and you look at the console in Eclipse, you'll see there's all sorts of information that's printed out. All that information is contained in the exception object. Right? There's lots of exceptions you can throw. Right? We've been using illegal argument exception a lot. We used index out of bounds exception on one of the assignments. If you have a null reference and you call a method with a null reference, you end up with what's called a null pointer exception. So we'll just skip over this. Okay, so this is where the last lecture ended. So those are preconditions, right? Those are conditions, something that must be true before a method is run. Right? There's also postconditions. So these are conditions that are true after the method finishes running. Right? Now, because they're true after the method finishes running, it's the responsibility of whoever's writing the method to ensure that the postconditions are satisfied. Right? So in other words, the postconditions are just a way of formally expressing what the method or constructor actually does. Right? So it's actually a mathematical expression of the contract of the method. If the postcondition is not true, then something went wrong in your method. Right? So either you've implemented the method incorrectly, you run the method's run where the preconditions weren't satisfied, or something strange has happened. Right? Okay, so what can a precondition involve? If you have a non-static method, right, then the precondition can involve all of these things here. Right? So if the method says it returns a value, there could be some condition on the value that's returned. If a method changes a field of the object, right, so it changes the state of the object, then there can be a condition on the state of the object after the method runs. And then finally, some methods will take in a reference to an object and then change that object. Right? So you can write a method that takes a list and sorts the list, for example. Right? So that method actually changes the state of the list. Right? So there's a postcondition on the state of the list after the method finishes running. Now, unfortunately in Java, there's no way to formally express a postcondition. So normally what happens is your postconditions are described in the documentation of the method. And they're normally not described as conditions. Right? So it's not the mathematical description of what the method does. Right? It's some English language description of the contract of the method. Right? So for example, here's our x method in the point2 class. Right? All this thing does is return the x coordinate of the point. Right? So that's normally, right there, the return statement there. Right? That's normally how you express a postcondition in Java, right? When you write the documentation for it. So that's basically the simplest method you can write, right? I don't think you can, it's probably not possible to write anything simpler than that, because all we're doing is returning the value of one of the fields. Okay. Now, it is actually possible to express the return value of this statement mathematically. Right? So it's possible, but it's awkward. Right? It's awkward to do. So for that little one-line method, right, we can rewrite this method so that you can actually say mathematically what this method does. It's surprisingly complicated, and so that's what it ends up looking like. Right, so here's our x method that's written so that I can express my postcondition. Right, so let's look at the postcondition first. Right, so remember, a condition is something that evaluates to true or false. Right, so this is just a Boolean expression down here. Right, now what does this expression say? It says, right, so this x, right, that's the x coordinate of this point, is equal to old x. Right? Now what's old x? Well, old x is the value of the x coordinate when the method first started running. Right? So this is saying that the method does not change the x coordinate of the point. Right? The next part, this y equals old y. Right? So this y is the y coordinate of the point. Oh wait, not old dot y. That's old big capital Y, sorry. Right? So what's old y? Well, old y is the y coordinate of the point when the method first started running. Right? So this is saying that the method does not change the y coordinate of the point. And then finally, the last part is this x equals the result. Right? So what's the result? Well, the result is the original x coordinate of the point. Right? And so this is saying that the return value is just the x coordinate of the point, which did not change inside the method. Right? So that's the actual mathematical description of this method. You can see here that this method contains an error in it. Right? So this method actually changes the y coordinate of the point. Right? So that postcondition is not satisfied, probably not satisfied. Right? Because so if the y coordinate of the point was not originally 0, then this method is wrong. Right? And so you can actually detect that if you were looking at the postcondition. Right? Now you might wonder why you might want to do this sort of thing. So postconditions, there are languages where you can actually write the postcondition and then the language will actually check if that postcondition is true after every method, after the method finishes running. Right? So in these languages that are used in mission critical applications, right? So anything where life or a lot of money or something is on, or something important is on the line, right? There are languages that actually support this sort of thing. Right? So where the correctness of a program is of paramount importance, there are languages that actually support this sort of thing. They also support precondition checking. And it's all automatic as long as the programmer writes the conditions that must be satisfied. Right, so this is all related to something called formal methods. So formal methods are the use of mathematical techniques to prove or to help write software correctly. Right, so you can actually formally prove that your program is correct in some cases. Right, but what it involves is writing stuff like this, and then checking pre and post conditions before and after all your methods run. Okay, so if you have so that method is an accessor method, right? So that's a method that just returns the x coordinate. So what about a method that changes the coordinate of a point? Right? So the post condition for a mutator method, those involve the fields of the object. Right? So here's a method x that changes the x coordinate of the point to new x. Right? And so it's simple to write. It's just this x equals new x, and then we return a reference to the point. Again, right, so that's a very simple method to write. If you try to write the post condition, it becomes surprisingly hard. Oops, sorry. Here we go. Right. So again, there's an error in this method. We'll get to that in a second. Let's look at the post condition. Right, so the post condition says that this x, so the x coordinate of the point, is equal to param x. So what's param x? Param x is the value of new x. Well, actually, this is, let me change this slide quickly and comment on that first line. Okay, so what's param x? Well, param x is the value of the parameter when the method first started running, right? That's what it's supposed to be, right? It's supposed to be the value of the parameter when it first started running. This y equals old y, right? So that's the same as the previous slide. Old y is the y coordinate of the point when the method first started running, right? So this is saying the y coordinate of the point does not change, right? And then it's saying, and then this equals result. So that's, what's result? Well, result is just a reference to the point, right, which is good. So this equals this point is true, right? So that's trivially true. Okay, right, so now let's look what happens. So in this case, if you check all of these post conditions, right, they're true. If you uncomment out that first line, though, the post condition is not true anymore, right? So here, in Java, you're allowed to change the value of a parameter. Right, so that parameter new x, as far as the compiler is concerned, that's just a variable that belongs to this method. Right, so inside the method, you can change new x. Right, so I can set new x to 1, for example. Right, now if my coordinate of the point, new x equals 1. Right, so if someone passed in a value of 5 for new x, right, then this method is obviously wrong because this ends up setting the point to the value of the coordinate to 1, the value of the x coordinate to 1 instead of 5. Right. So this is actually the slide that I wanted to show you. So the reason you have to put these two lines here, they have to be the first two lines in the method in order to prevent mistakes like this. Right. So really, the way you want to write this is as follows. Right. You want, you want to remember, right, what is the original value of the parameter. You want to remember what's the original coordinate of the point. Right. In the previous example, we had to remember what was the original coordinate of the original value of the x coordinate, right? So there's a bunch of setup that you have to do, and then there's a condition that you check at the end, right? Now here, if you change new x inside the method, and then set this x to new x, right? This post condition down here is probably not true, right? Unless you happen to call the method with 1, right? So you can in fact write this post condition, right? Even for a trivial method, it's awkward to do. So you can imagine if you had a method that's somewhat more complicated, writing the post condition is not easy to do, which is why it's not commonly done unless there's something important, right? Unless you're writing mission critical software. Oops, sorry. Okay. Now, is there any way to actually check the post condition? In Java, the answer is there's no correct way to do it. The closest that you can come is you can, before the method ends, or right before the method ends, you can write some sort of if statement to check the post condition, and then throw an exception if the post condition is false. Right? Now the problem with this is that every time someone calls your method, they end up having, the post condition ends up being checked. Right? And if you have a very complicated post condition, that can take a long time to check. So the way this looks is as follows. right? So again, this is using a different version. This is using the method set, right? So this is using the wrong method, actually. Sorry. That's supposed to be the method x. Okay, so that's using the previous example. Oops, sorry. Right, there's our post condition right here, right? The stuff inside the brackets, right? You want to check if that post condition is false, so you negate the entire post condition, right? So this is saying if the post condition is false, throw an exception. The post condition is false, right? So you can, in fact, check. You can check it by putting in your own if statement this way. This actually isn't correct, because what you really want to do is you want to check the post condition right here, immediately after the return statement. Right? This is where you want to check your post condition. But you can't do that in Java because you can't have any code after a return statement. So the languages that actually check post conditions, they are capable of checking the post condition at the point where the method actually ends. Right? Java, unfortunately, is not one of those languages. All right, so you can, instead of using an if statement and throwing an exception, you can use assert. Now, I don't know if you've seen assert in C. Did they teach you the assert statement in C? Yes, no, no, yes. Okay, so the assert statement in Java works the same way as it works in C. Right? So in the assert statement, you pass in a condition. If the condition is true, nothing happens. If the condition is false, then you end up with an error. Right? So an error is different than an exception, but they're close enough that we can call them the same thing. Right? So an assertion error will actually cause your program to stop. Now the thing with assertions is you can turn them on and off. Right? So you can write the code, you can write the assert statement, put in whatever code you need, but then you can turn that assertion on or off using a compiler flag. Right? So the way you use assertions is when you're developing your code and testing your code, you turn your assertions on, right? So that helps you actually check your code as you're writing it. When you're ready to ship your code, you turn the assertions off, and that way people don't have to pay the price of checking the post condition every time the method runs. Right? So the way it looks is just like this. Right? So it's just assert, round bracket, and then your condition that you want to check is true. Right? So here you just assert the post condition, and away you go. Right? In Eclipse, assertions are turned off by default. So if you wrote this code, right, even though it's wrong, right, even though we set new x to 1 and then set x to new x, right, this will never cause your program to crash, right, because by default they're turned off in Eclipse, right. So to turn them on, you can just do this if you want to use assertions in your program, right. We're not actually going to use these in the course, but if you want to use them in your programming, you need to know how to do that. All right, so that's post conditions. There's one other kind of condition that's important, and these are called class invariants. Okay, so an invariant is a condition that's supposed to be always true. Right? A class invariant is a condition regarding the state of an object that's always true. Right? So in other words, it's a condition on the fields of the object. Right? Those conditions should always be true. Right? Now, because they're conditions on the fields of the object, right, your constructors for your class have to ensure that the invariants are true after the constructor finishes running, right? Because the constructor initializes the state of the object, right? So if it incorrectly initializes the state of the object so that the invariants are not true, you've got an invalid object. Okay, similarly, if you call a method on the object, that method has to ensure that the invariants are true after the method finishes running, right? Otherwise, you have an object that's in an invalid state. Right? So what's an example of a class invariant? Well, point 2 has no interesting invariants. Right? So point 2 is just an x and a y coordinate, right? There's no conditions on the x or y coordinate of a point. But that counter class that we've been talking about, right? Remember, the counter is just this thing that counts from 0 up to integer max value. Right? That does have a class invariant. Right? So in other words, the value of the counter is always between 0 and integer max value, right? Because that's what the class promises, or that's what the class says it's trying to do. Right? So if you look at the implementation of counter, right? So if you look at its constructors, if you look at its methods, right? You can verify that these are in fact always true. Are we going to do that next? Yeah, we're going to do that a little bit. Okay, so how do you check a class invariant? So these things are true at the end of every constructor or method, right? So you can use the same technique that we use to check a postcondition. You can use an assert statement or an if statement to check that the invariants are true, right? Now, your invariant is always the same condition, right? So postconditions are different for every method. The invariant, these are things that are always true. So you can just write a method, right? Here I've got a private method called checkInvariant that simply checks the invariant, right? So what does the code look like? Well, it's just going to assert that the value of the counter is always greater than or equal to 0, right? I don't have to check if the value of the counter is less than or equal to integer max value, right? So why don't I have to do that? Because value is an int, right? And the largest int that you can have is integer max value. So I don't actually have to check the upper bound here, right? I only need to check the lower bound. And now, in every constructor, at the very end, right, on the last line, right, you just call your checkInvariant method, right? So the counter no argument constructor sets the value of the counter to 0. Check the invariant. Is the value of the counter greater than or equal to 0? Yes. So everything keeps running as normal, right? Here's a constructor that sets the value to the specified value, right? Checks the invariant at the end. Now, how does this constructor ensure that the value of the counter is always between 0 and integer max value? It actually checks the incoming parameter, right? So here's an example of a constructor that actually has a precondition, right? And it's an example of a class that has an invariant, right? The precondition is that that thing there has to be greater than or equal to 0. The precondition is there in order to satisfy the class invariant, right? So we check. Right? Is the value less than 0? If it is, we throw an exception. Object's never constructed. Everything's good. Right? If the value is greater than or equal to 0, we go ahead and set the value to the specified value, and away you go. There's the constructor that checks, that copies another counter. Right? So we copy the other value from the other counter. Right? Again, you can check the invariant at the end of the constructor. And then not this one. Not allowed. Oh, right. If a method returns a value, right, you have to check the invariant before the return statement, which is actually a problem, because if someone inserts some code in between these two lines, you aren't guaranteed that the invariant's actually true, right? And this is because you really want to check the invariant here after the return statement, right? But you can't do that in Java. So you have to check it before the return statement, right? If someone else comes along and inserts code after that invariant check, right? So in other words, if they change the value to say -1, this doesn't help, right? Because your invariant's true, someone else screws up your code, makes the invariant false, but there's no way to check that invariant anymore, right? So again, in the languages that support in languages that support invariant checking, they will actually check the invariant. They insert the check for the invariant automatically, right? So there's no way for the programmer to screw up the check. And then finally, advance, right? So this is the method that increases the value of the counter by 1, right? Does it ensure that the value of the counter is always between 0 and integer max value? Well, you just look at the code, right? So if the value is not equal to integer max value, add 1, right? That's fine. Right? If you add 1 to integer max value, you get a negative value, right? So you want to prevent that from happening, right? If you are equal to integer max value, you set the value to 0, which is also fine, right? The invariant's still true, right? The other thing that you know in this method is that the value is never negative when you come into the method, right? Because you've checked the invariant at the end of every constructor and method. So you know that it's not negative coming in, so you should be fine going out, right? So everything's fine here. And then finally, here's toString, right? So again, toString's got a return statement in it. I want to check the invariant here, but I can't. So I have to check it immediately before the return statement and hope that someone doesn't come along and insert some code between these two lines. All right, so that's preconditions, postconditions, and class invariants in Java. So these are all important. Well, they're all important in programming in general. but they really show up in something called formal methods, right, which I talked about earlier. You guys, I don't think, will ever actually see a formal methods course. So I don't think there's any way for you to take the fourth year computer science course that actually talks about this sort of stuff. Right. If you're interested, though, there is a course in the computer science department that talks about how to formally check a program for correctness. Okay, moving on to the next lecture. Does anybody have any questions about preconditions, postconditions, invariants? All right. Okay, so remember when we started the course, I told we started out talking about methods, which are sort of like I started talking about static methods, which are sort of like C functions, right? And then when we started talking about objects, everything moved away from static stuff, right? And now we're back to static stuff again, right? So the classes, like our counter class and our point class and things like that, right? Everything inside of those classes so far, the methods have all been non-static, right? But you are allowed to have a static method or a static field inside of any class, right? Now remember what static features are, right? So a static field, right? That's a field that belongs to the class, right? And a static method, that's a method that belongs to a class, right? You don't need an object to access the field or the method. Right? So static fields are what are called per class members, right? There's one field for the entire class, right? Only one copy of the field. That field's associated with the class. The individual objects do not have their own copy of the field. In other words, every object that you make using that class shares the exact same field. Right? They all have access to the exact same field at the same time. Right? You sometimes see these called class variables. Right? So in other words, a variable that belongs to the class. Right? But I'm always going to call them static fields. So if you've been reading the notebooks, you will have encountered this domino class. Right? So the domino class just represents a domino. Right? If you don't know what a domino is, it's just a playing tile, right? It's got two sides, and the numbers, the value of each side of the domino is something between 0 and 6 on a standard set of dominoes. Right? So you can write this little class that represents a playing tile, a domino, right? The playing tile. If you look at the implementation of the class, you'll see that there's two static fields. There's a public static final field called min value, right? Its value is 0. And there's a public static final field called max value, whose value is 6. Right? So that's just the minimum and maximum value that a domino can take. Right? And that's exactly analogous to integer min value and integer max value. Right? Smallest minimum value, smallest value that an integer can take, and the largest value that an integer can take. Right? So exactly the same thing. They're public because anybody using this class might want to know what's the smallest domino value, right, and what's the largest domino value. They're static, which means there's only one copy of this field, right? Why is there only one copy of this field? Because the value is the same for every domino, right? So it doesn't make sense to store that value or these two values for every domino object, right? I only have to do it once. So the way you do that in Java is you make the field static. Right? It's final. Remember what final means? A final field can only be assigned a value once. Right? So when I write min value equals something, right, that's the only time that's the last time that I can assign a value to min value. Right? So in this case, min value is a constant whose value is 0, max value is a constant whose value is 6. Right? I've got two non-static fields here, right? Val1 and val2. Those are just the two sides of the domino. Right? So for this domino, val1 would be 5 and val2 would be 5. Right? For this one here, so how about here, right? You'd have 1 and 3 as val1 and val2, right? So val1 and val2, those have to be non-static, right? Because every domino has its own two values. Okay, so if you want a picture of what this looks like, you can draw a little memory diagram. Right? So if I make two domino objects up here, right? So there's D1, it's the domino 1, 3, right? D2 points to the domino 5, 5. Right? So if you look in the memory diagram, there's a domino object here, right, whose values are 1 and 3. There's a second domino object here whose values are 5 and 5. right? Val1 and Val2 are non-static, right? So both domino objects have their own copies of Val1 and Val2, right? Min-val and max-val are static, so there's only one copy of these two fields in the entire, in memory, right? And they live inside the domino class, right? So in other words, this domino here does not have a copy of min value and max value, right? That domino here does not have a copy of min value and max value, right? So that's what a static field is, right? It's a field that belongs to the class. You already know this, right? So whenever you access a static feature, you use the name of the class to access the static feature. So if I want to use min value, you write domino.min value. Right? Now, what I haven't told you yet is that you can actually use an object to access a field, a static field. Right? So you can make a domino object here. Oops, sorry. You can make a domino object here, and then write d.min value here, and this works fine. Right? The compiler doesn't complain about this. Right? So this is legal, but it's considered bad form. Right? So in other words, it's a stylistic programming error. Right? An experienced Java programmer who reads this will have something to say to you. Right? If it's your boss, they'll have something bad to say to you. Right? So if you're accessing a static field, remember that you should always be using the name of the class to access the field. A final field, so final means that you can only assign a value to the field once. Right? Now, min value is a primitive value. Right? So remember how primitive values work in Java. Right? So primitive values in Java, right, or primitive variables in Java, they actually store the value that you assign to them. Right? So min value here stores the number 0, max value here stores the number 6. Right? Marking these final means that I can't change the 0 and I can't change the 6. Right? So a public static final field, that's actually a constant if it has a primitive type. Right? So whenever you see a public static final field in a class, right, number one, it'll be documented because it's public. Right? Two, it's supposed to be a constant. Right? And it's supposed to be something that's meaningful to the class. Right? Min value is meaningful to the domino class. Right? It's the smallest domino value. Right? Pi is meaningful to the math class. Right? It represents the value pi. So if you have a final field of primitive type, it's a constant. If you try to change it, right? So in other words, if I try to write domino.min value equals 100, the compiler will not compile that program. Right? You'll get some sort of error saying that min value is final and already assigned. Right? So that's great. Compiler will check that for you. Right? Now remember, we also have reference type variables. So if I have a public static final string called x, right, is this also a constant? Right? It turns out yes, it is, because string is immutable. Right? So remember, the string class has no methods that can change the contents of a string. Right? So when I make the string peekaboo, right, there's a string object somewhere in memory that's forever peekaboo. Right? Can't change the p, the e, the k, or anything else in it. Right? So there's some object whose value I cannot change in memory. Right? Now x points to that object, and it's final. Right? So that means that x always points to that object. So if you try to change x so that it points somewhere else, that doesn't work. Right? Again, the compiler will complain. Right? It'll tell you that x is a final field. Right? It's already assigned. Right? So you can't. So a public static final field of reference type, where the type is immutable, is also a constant. Right? Now, what happens if you have a type that's not immutable? Right? So remember, the list interface, right, has methods like add and remove. Right? So you can actually change the contents of a list. Right? If I try to make a public static final list called empty that represents an empty list, right, does this actually work? The answer is no. Right? It's not logically constant because you can do something like this. Right? You can take that list and add something to it. Right? So I can add the string oops. Right? And your empty list is no longer empty. Right? And this works just fine. The compiler does not flag this at all as being an error. Right? So your thing that's empty is no longer empty, right? Which means that name doesn't really make any sense, right? So a final field of a mutable type is not logically constant, right? Because you can change that you can change the state of that object. Right? So in other words, don't do that, right? So don't make a public static final field whose type is a mutable reference type, because you can change the state of that object, right? And it's not constant, right? So public static final fields are meant to be constant values, right? If you do end up doing something like this, right? Number one, don't call it empty, and number two, document the fact that this thing might change, right? In other words, document the fact that this is in fact not a constant. Okay. Now, what about static methods? So can you have a static method in a class, right, that has non-static stuff in it? The answer is yes, you can. Right? So a static method is a method that belongs to the class. Right? You don't need an object to call the method, you just use the class name. Right? These are also called class methods, but I'll always refer to them as static methods. Right? So the domino class has a method called isValueOK. Right? All this does is check if that integer value there is between 0 and 6. Right? Now, the method is static, right, because you don't need a domino object to check if that value there is between 0 and 6. Right? In other words, this method here is not related to any domino in particular. Right? It's not related to any domino object in particular, so you can safely make it static. Right? The other way to think about this is I don't need access to this dot val1 or this dot val2. Right? If you don't need access to fields of a domino object, then make it static. Right? So the implementation of the method is simple, right? You just check is value greater than or equal to min value, and is it less than or equal to max value. Right? To call the method, you use the name of the class, right? And you already know that. Just like static fields, it's legal but considered bad form to use an object to call a static method. Right? So you can make a domino object here, and then use that object to call a static method. Right? Again, you should avoid doing that. Right? If you have a static method, you should use the name of the class to call the static method. All right, so where are static methods and fields used? So one place that they're used are in these things called utility classes. But utility classes are relatively uncommon in Java. Right? So remember what a class is. It's a model of it's just a thing, right? It's a model of a thing or concept, right? You're trying to make a type. It's a user-defined type. Right? And you use the class to make objects, right? That's normally what you use a class for, right? But you don't have to. You don't have to make a class that's used to make objects, right? So sometimes it's useful to create a class called a utility class where you're not making objects, right? So if you're not making objects with this class, there's probably no constructor in the class, right? Because you need a constructor to make an object. If there are no objects, then you can go ahead and make everything static, right? So that's the easiest way to determine whether or not a class is a utility class or not, right? Just look at the documentation. If everything's static, it's probably a utility class, right? Now, these are by far the less common type of class in Java, right? Normally, classes are not utility classes, but there are some important utility classes in the standard library, right? So the math class, that's an example of a utility class, right? It's got some constants, pi and e, right? It's got a bunch of static methods that do some sort of mathematical operation, right? But there are no math objects, right? Arrays is just a bunch of methods that operate on arrays, right? And collections, just a bunch of static methods that operate on lists and sets. Right? So why would you want to make one of these things? Well, the reason for making a utility class is you want to group together fields and methods where you don't need to make an object. Right? So math groups together mathematical constants and functions, mathematical functions. Right? You don't need a math object to compute the cosine of a number, for example. Right? So math can be a utility class. Right? The class collections groups together methods that operate on Java collections, right? So in other words, they have methods that take in things like lists, does something to the list, right? you don't need a collections object to do something to a list object. So if you're making one of these classes, the point of the class is to not make objects, right? So you never use the class to make objects. And so when you use a utility class, only the class itself ends up in memory, right? So for example, if you use the math class, right, all you do is write math.blah, right, and math.cos and math.sine, right? If you want to use pi, you just write math.pi, right? Nowhere in here do you make a math object, right? So nowhere in here do you write math m equals new math, right? If you look at the memory diagram for this program here, right, all that you find in memory is the class itself, right? So there's the class, there's its static fields, pi and e, right? There's no math object, right? There's a value x and there's a value y, right? No math objects here, right? So how do you make one of these things? Well, it's easy. You just make a class and you make everything static, right? So you can make a little utility class here that lets you calculate E equals mc squared, right? Einstein's mass energy equation, right? It's pretty easy to do. You just make a class just like you'd make any other class, right? So I'm going to make a public class called relativity, right? If you want a package, make a package. Right? Okay, now what do I need to calculate E equals mc squared? I need the speed of light, right? Speed of light's a constant. It's actually a physical constant. So in this case, it makes sense to make it a public static final field, right? Because other people might want to use the value of c, right? Especially if they're using your relativity class. So I've got a public static final double field called c, and its value is that, right? So that's the SI value of the speed of light in meters per second, right? And then I have my equation E equals mc squared, right? So so I'm calling that mass energy, right? It returns a double, right? It's static, right? Because I don't need a relativity object to compute the energy equivalent to that amount of mass, right? How do you write the method? Well, it's just mass times c squared and return that value, right? Easy peasy, right? There's nothing to it, right? In other words, I mean, we've done all this before, right? If you want to use the class, right, well, you know how to do that too, right? It's a utility class, so everything's static. So to use the mass energy function method, right, I use the name of the class, right? Name of the method, pass in some amount of mass, right, in kilograms, right? So if you pass in a mass of 1 gram, run the program, you get that number there, right, which is enormous, right? You're all engineers, right? That's 9 times 10 to the 13, right? You should recognize that's a huge number, right? That's 1 gram of mass converted into energy, right? That's the amount of energy that was released by the atomic bomb dropped on Nagasaki, right? So converting just a tiny amount of matter into energy releases a huge amount of energy, right? Which is why nuclear reactors are cool, right? Okay. Now, notice our class. There's nothing in it, right? There's just there's a field here. There's a method here, right? Nothing. There's no constructor, right? So there's no constructor, but if you remember from our discussion earlier, right? If you don't put a constructor in the class, Java sticks one in for you. So unfortunately, you can in fact use our class to make a relativity object, right? Because Java inserts the no argument constructor for you, right? But you already know that, and so the constructor that you end up with looks like this, right? You get the no argument constructor, it does nothing, right? Because this thing has no non-static fields, right? So you should prevent this from happening, right? The point of using this class is not to make objects. So I would like a way to not make objects with the class, right? So what's the solution? You write a constructor and you make it private, right? So a private feature of a class cannot be used outside of the class, right? So if you make a private constructor, anybody outside of the relativity class cannot call that constructor. If you put any constructor into a class, Java does not insert the no argument constructor for you. Right? So the way you do this is you insert a private constructor that does nothing, right? So it's private and empty by design, right? Making it private means that nobody can call the constructor, right? Unless they're inside the relativity class, right? By adding our own constructor, Java doesn't put one in for us, right? So now, if you try to make a new relativity object, it doesn't work, right? Because that constructor is private, right? And that's how you make a utility class, right, in like 5 minutes. It's very easy to do, right? Everything's static, add a private constructor, right? And that's the end of the story. So whenever you make a utility class, always make sure that it has a private, empty, no argument constructor, or some other constructor, it doesn't matter, right? And that prevents people from making objects using your class. Okay, so I'm going to stop there. I have a meeting to get to at 9:30. We'll talk about these things next. So these static factory methods, these turn out to be very common in Java. Right? So this is a very common use of static methods in the Java programming language. And we'll talk about that on tomorrow, I guess. All right.